Okay, welcome back. Did you think about that question we asked last time? Okay, so question we asked last time, are the following measurements the same or different? So we've got 5 kilograms, we've got 5.0 kilograms, and we have 5.00 kilograms. Same or different? What do you think? Well, it turns out they're different. Okay, why are they different? Isn't 5 and 5.0 and 5.00, aren't those exact same numbers? Yeah, they are the same numbers. Okay, but that wasn't the question. The question is, are they the same measurements? And there actually is a difference. Now, in your math class, you'd ask your teachers, 5 and 5.0 and 5.00 the same thing. They'll say, of course it is. It's the same thing. And I agree. They are the same numbers. But when you're dealing with measurements, they imply different things. Okay, it's a question of what we call experimental error. Okay, anytime you measure something in the laboratory, there's going to be some error involved. You know, you've heard the phrase, nobody's perfect. Well, that's true. Nobody is perfect. You know, we all make mistakes. And let's just say hypothetically you are perfect. Let's say you never make a mistake. Well, the problem is the things that you're measuring with make mistakes. And so even the machines that you use are not perfect. So experimental error is kind of a fact of life. It's just something that you have to deal with, you know, if you're going to be a scientist. All right, so what makes these three measurements here different? Well, if I had a scale here that weighed something as 5 kilograms, well, it's giving me one place here, okay? So the true measurement of the object is somewhere between 4.5 up to, but not including, of course, 5.5, because that would round to 6. All right, and the scale is just showing me 5 because it's rounding off to the nearest 1 here. This one weighs things to the nearest tenth of a kilogram. So the true weight of this object could be anywhere from 4.95 kilograms up to, but not including, 5.05 grams. Of course, that would round to 5.1. All right. And then this scale over here maybe measures things to the nearest hundredth of a kilogram. And so the true weight of the object is somewhere between 4.995 kilograms and 5.005 kilograms, not including that, of course. All right. So although these are the same numbers, these measurements imply a different accuracy. You know, if you put something on a scale, you know, what are the odds that that thing actually weighs 5.00000 out to infinity kilograms? Well, you know, slim to none. So what that scale is doing is rounding off. So in that sense, these three measurements actually mean something different. The key is there I said measurements and not numbers. All right, so this is pretty much the same thing, but let's just go through it here. So suppose an object's weighed on a crude balance, and crude in chemistry would be plus or minus a tenth of a gram, and its mass is found to be 23.6 grams. This measurement contains 3 experimentally meaningful digits. See, I got the 2, I got the 3, got the 6. All right, or what we call 3 significant figures. All right, on a more accurate balance, the mass might be 23.573. See, this is one that maybe rounds off to the nearest thousandth of a gram here. Okay, 5 significant figures, 1, 2, 3, 4, 5. So which one of these measurements is more accurate? Does the object weigh 23.6 grams? Or does it weigh 23.53 grams? Because I got 2 scales that are telling me something different. Which one's right? Well, neither of them are right. What are the odds that the object actually weighs 23.5730000 out to infinity grams? Well, practically 0 there. More than likely it's rounding. Well, it is. It's probably rounding off here at the thousandth of a gram. All right. So, yeah, all the questions in chemistry are all trick questions, by the way. So neither of these is actually the correct weight of the object. Which one of these measurements is closer to the true value? Well, the 23.573, right? Okay. How many significant figures do I have here? 5. How many significant figures do I have here? 3. Can you give me a rough general rule of thumb for the accuracy of a measurement and the number of significant figures? Well, the more significant figures you have, the more accurate the measurement is. It's that simple. So all you have to be able to do is count. If you can count, you can do significant figures. All right? And so that's what we're going to talk about, is we're going to talk about significant figures and experimental error. Are there more sophisticated ways to calculate experimental error with standard deviations and all sorts of things like that? Yeah, there are. Do you need that? Not now. Maybe if you take a good class in analytical chemistry, you'll talk about some more sophisticated statistical methods, or take a stat class. That would be the most direct way to do it. But significant figures will carry you pretty far down the road, and it will carry you far enough down the road to do what we're going to do here. Okay? All right, so how do I know if a figure is significant? Well, it's pretty simple. If it's a 1 through 9, always counts. Always. The only time you have to worry about it is if it's a 0. Sometimes the 0 counts, sometimes it doesn't. All right, so for example, volume of a liquid, 20.40 milliliters. How many significant figures do I have in this measured quantity? Well, I have 4. Okay, all of these numbers are significant. Why? Well, I know the 2 and the 4 are. The only things are the zeros I have to worry about. All right, and here's the rule. Zeros at the end of a measured quantity, following non-zero digits, or in between non-zero digits, count. So this 0 counts here. That's in between non-zero digits. But this 0 here counts as well. All right, why does this 0 count? Logically. Well, if I had left this 0 off, then I would be saying I'm measuring the volume of this liquid to the nearest 10th of a milliliter, right? The 0 at the end here implies that I am measuring to the nearest 100th of a milliliter. And of course, that's going to be more accurate. So zeros after non-zero digits, after the decimal point, that's actually kind of key there, count. We'll talk about it. Okay, let's try it again. Here's the volume of a liquid, 0.02040 liters. How many significant figures do I have in this particular measurement? Well, I have 4 here as well. All right, so I've got 6 numbers here. 4 of these count, 2 of these don't. Which 2 don't count? Well, it's this one and this one, the ones with the X's above them. Those don't count. These do. All right, so why? Well, here's the rule. Zeros at the beginning of a measured quantity preceding non-zero digits are not significant. So these zeros are at the beginning of the quantity, and they start before my non-zero digits start, so these 2 don't count. They're placeholders. This is in between non-zero digits, so it counts. This is after non-zero digits, after the decimal place, so it also counts. So these 2 count, those 2 don't, according to the rules. Okay, why? Well, let's say, for example, I had a measurement here, 0.000001 grams. All right, and how many significant figures would I have there? Well, I have 1 significant figure. You might say, but if you measured something in near 0.00001 grams, wow, you made a really accurate measurement there, so how can that only be 1 significant figure? Well, it's 1 significant figure because, yes, you didn't make much of an error, but the thing that you're measuring is also tiny. If you measured a truck to the nearest 3 grams, hey, that's pretty good. If you measured a paper clip to the nearest 3 grams, well, that's pretty bad because a paper clip weighs about 1 gram. So if you're plus or minus 3 grams on a 1 gram object, that's pretty poor accuracy there. And so it's all about relative error. Okay, what you're measuring counts, the total value. And so in the case of this one right here, say for example, you've only got 1 significant figure because, yeah, these don't count. So relatively speaking, it's a relatively precise measurement, or rather inaccurate measurement, I suppose, even though you made a very small mistake. See? All right, so these are just placeholders. You don't count those. All right, and if there was a 1 here, then yeah, all of them would count because these would be in between non-zero digits. Make sense? Okay, one more. So, 3,000 grams. How many significant figures? Are there 1? Are there 2? Are there 3? Or are there 4? Well, congratulations. Whatever you answered possibly correctly. It depends. Okay? There won't be 5. If you answered 5, that's not right. All right? But it could be 1, it could be 2, it could be 3, or it could be 4. All right? These are zeros after non-zero digits before the decimal point. Okay, and these might be significant, might not. It's ambiguous. All right, how do I tell people, hey, all of these count? Well, one way you can write is you can write it like this. See, you can put a point after that, and when you see a number like this, that means, hey, all these things count. 1, 2, 3, 4. You could also write a number like this. Here's a 0 after non-zero digits after the decimal point, so I know this one counts, and if this one counts, that means these three have to count too. So these would actually have 5 significant figures. But what if I want to say, hey, I measured this to the nearest 3,000 grams, and I rounded off to the nearest 10 grams? In other words, these three counted, but that one doesn't. Or what if I want to say I measured this to the nearest 3,000 grams, and I rounded off to the nearest 100 grams? In other words, these two count, and those don't. Or maybe none of these count. Maybe I rounded off to the nearest 1,000 grams. Well, when you run into a situation like this, it's best to put your number in scientific notation. Because the nifty thing about scientific notation is everything in front of the times 10 to the always counts. You don't have to worry about it. All right, so if I wanted to say, hey, 3,000 grams plus or minus 500 grams, somewhere between 2,500 and 3,500 there, then I would move my decimal back toward the first non-zero digit. So that's 1, 2, 3. So this would be 3 times 10 to the. Okay, I went 3 places, and this number is greater than 1, so it would be 3 times 10 to the third. And I would write it as 3 times 10 to the third, one significant figure. If I wanted to say, hey, these first two count, but the last two don't, I would write it as 3.0 times 10 to the third. And that's 3,000 to 2 significant figures. If I wanted to say 3,000 to 3 significant figures, in other words, these three count and this one doesn't, then I would write it as 3.00 times 10 to the third. And if I wanted to say they all counted, I'd write it as 3.000 times 10 to the third, 4 significant figures. The nifty thing about scientific notation is all my numbers in front of the times 10 to the count. The bad thing about scientific notation is sometimes it's kind of cumbersome to deal with. So we like to write numbers in regular form. 2 times 10 to the 0 plus 2 times 10 to the 0 is equal to 4 times 10 to the 0. But nobody really says that. Make sense? So sometimes you'll be looking in the back of the book, you'll be doing your homework problems, and you'll look in the back of the book, and the answer you'll see in the back of the book is 8 times 10 to the first grams. Well, what is that? Well, that's 80 grams. So why are they calling it 8 times 10 to the first? Well, they're trying to tell you it's 80 grams to one significant figure, not two. All right? So when in doubt, put it in scientific notation. If there's no doubt, don't worry about it. Would I ever throw something like this at you on a test? No. There are ways around that. I could do something like this, put a 0.0, to make sure you know there that it's, that number of significant figures. But no, I wouldn't throw this at you and expect you to know how many significant figures are in that particular measurement. Okay? All right, can you count significant figures? Okay, when we go into the laboratory, we don't just write data down and go home. We do stuff with data. We do mathematical calculations with data. So what are some mathematical calculations we can do with data? Well, there's a couple of things you could do. You could multiply or divide, okay, or you could add and subtract. Well, if you think about it, multiplication and division are kind of the same thing. Division is multiplying by the reciprocal, right? And subtraction is just adding the opposite. So therefore, there's a rule for multiplication and division, and there's a rule for addition and subtraction. All right, so what is the rule? Well, when you're multiplying and dividing, the rule is keep only as many significant figures as there are in your least precise quantity. All right, so for example, what is the density of a piece of aluminum weighing 46.675 grams with a volume of 17.3 milliliters? Okay, well, I know that density is equal to mass over volume, right? Okay, so do I know the mass of my aluminum? Well, yeah. It's 46.675 grams. Okay, do I know the volume? Yeah, it looks like it's 17.3 milliliters. So all I got to do is divide here. Okay, notice I have grams up here on the top. I have milliliters here on the bottom. What's going to be the units of my answer here? It's going to be in what? Well, grams per milliliter. All right, so I run it through the calculator, and the calculator tells me that's 2.697976879 grams per milliliter. All right. Do I really know the density of that piece of aluminum that accurately? Well, no, I don't. A lot of those numbers that are coming out of my calculator are just garbage, right? Just kind of random numbers. But, I want to put all those down if I can, so I'm going to write 2.69797689979 in a scientific paper. Well, if I write that in a scientific paper and someone looks at that piece of data, what are they going to think? They'll think, wow, he really measured that accurately. I'm going to write that down and use that. When in reality, you didn't. All right, so you always want to report numbers as accurate as you are sure of, and you don't want to go further because you don't want to be fooling people or fooling yourself sometimes. All right, but at the same time, you don't want to say, well, it's about 3. You went to all that trouble to measure things really carefully and use expensive equipment and this and that, when you could have just, well, it's about 3. You could have guessed that, right? So you want to get as much accuracy out of the stuff that you're using and the time that you put into it, but you don't want to go too far. So as a wise man once said, I believe it was Dirty Harry in Sudden Impact, a man's got to know his limitations. How do I figure out where to round off? And that's the question the intro to chemistry kids are always asking me. Where do I round off? Well, usually I'll just go about 2 decimal places and call it good. Because, if I told them this stuff, it would just pretty much blow their minds. So we're not going to go there. But with you, we are. So how do you know where to round off? Well, I'm dividing. The rule is keep only as many significant figures as are in your least precise quantity. All right, so how many significant figures do I have up here? Well, I have 5. How many do I have down here? I have 3. So how many significant figures should my answer have? Well, it should have 3. Okay, so how do I figure out to report this value? Well, I'm going to go 1, 2, 3, and then I'm going to look at the next digit. All right, if it's a 5 or higher, we're going to round up. If it's a 4 or lower, we're going to round down. Now, there's a rule that says if it's a 5, then you look at the number, and if it's an even, you round next number. If it's an even, you round up, and if it's an odd, you round down, or something like that. No, just if it's a 5, round it up. If it's a 4, round it down. Let's not get too complicated. And there's actually some debate as to whether that's actually worth the trouble or not. But you don't really care. 5 or higher, round up. 4 or lower, round down. You're going to be okay. All right. So in this case, I see a 7. So I guess it doesn't matter in this case, right? So I see a 7. Okay. So that means I'm going to round up. All right. So I'm going to round this up from a 9 to a 0 and change that to a 7. And so my 2.69 here rounds up to 2.70 grams per milliliter. 3 significant figures. Could I just call it 2.7? No. Can't call it 2.7 because 2.7 implies that you only know the density of that lumen to the nearest 10th of a gram per milliliter. 2.70 implies you know it to the nearest 100th of a gram per milliliter. See, 3 significant figures. And really, with the measurement values that you have, assuming you measure everything correctly, that's as far as you can go, no further. And that's how you know where to round off. Make sense? Okay, well, what if you're adding and subtracting? Well, here's the thing. What people will do is they will take the rule for multiplication division. They learn, you give a guy a hammer and everything's a nail. They'll learn the rule for multiplication and division, and then what they'll do is they'll just try to apply that everywhere they see it. All right. When you're adding and subtracting, it's a different rule. All right. The rule for addition and subtraction is keep only as many places past the decimal point as are in your least precise quantity. All right, so for example, a sample of that's potassium bromide, we'll talk about later, is placed in a beaker weighing 58.6 grams. The beaker and the sample weigh 59.253 grams. What is the mass of the potassium bromide sample? Okay, well, I know that the beaker and the sample weigh 59.253 grams. I know that the beaker by itself weighs 58.6. Can I just subtract off the weight of the beaker, and wouldn't that give me the weight of the sample? Sure. So I got 59.253 minus 58.6. Subtract that, I get 0.653. But do I really know it out to that third decimal place? Well, here I'm subtracting. So your rule is keep as many places past the decimal point as your least precise quantity. So how many places am I past here? 3. How many places am I past here? 1. So I really only know this out to the nearest tenth of a gram. So we're going to take this number. Here's my 6. We're going to look at the next number. The next number is a 5. So we're going to round up. And so this becomes 0.7 grams. One place. And that's as far as you need to report it. Okay? Now, why, logically? Well, what is this digit right here? Well, I don't know what that is, right? What's this digit right here? Well, I don't know what that is. What's 3 minus I don't know? I don't know. What's 5 minus I don't know? Well, I don't know that either. So do you see, I really don't know what these numbers are over here. All right, this is as sure as I can go, is this tenth of this one place here. And that's why the rule works. Okay? Now, what if you tried to apply significant figures here? How many significant figures do I have here? Well, I got 5. How many do I have here? 3. So how many should I have how many do I have in my answer? I only have 1. I have 3. All right, and this happens quite often when you're subtracting. Sometimes the number of significant figures decreases when you subtract. Is that okay? Yeah, okay. It's the way it is. All right. But it shows you can't use significant figures when you're adding and subtracting. Look, you have a rule for multiplication division. You have a rule for addition and subtraction. When you're adding and subtracting, use the rule for addition and subtraction. When you're multiplying and dividing, use the rule for multiplication division. Do not get those mixed up. All right. If you get those mixed up, you are going to miss the problem. 2 separate rules, 2 separate situations. Okay? Now, I know you can add and subtract. I know you can multiply and divide. I know you can count significant figures. But the question is, can you do them both at the same time? You know, it's kind of like patting your head and rubbing your belly. It's a little cumbersome at first, all right, but eventually you get used to it, and you just do it automatically, and you don't have to worry too much about it. It gets better. It's just a little bit awkward at first. All right, so practice. You will become very adept at this if you practice it. And the key is to remember that you're not dealing with numbers here. You're dealing with measurements. You know, I'm not trying to teach you some sort of new math that's totally different than what you learned in elementary school. You're doing error analysis, and that's why the rules work the way they do. You're not doing math anymore. Does that make sense? Okay. Well, do all measurements have error in them? Well, what if I said there are 60 people in your general chemistry class? When I say there are 60 people in your general chemistry class, do I mean somewhere between 60.5 and 59.5 people? Am I rounding off the nearest half of a person there? You ever seen half a person? Oh, God, that would be kind of gruesome. Right. When I say there are 60 people in your class, I mean there are 60 exactly people in your class. How many inches are in a foot? Well, 12. About 12? Close to 12? Sometimes 12? No, exactly 12. 12 inches in a foot. That's how a foot is defined, right? So it turns out there are some measurements out there that have no error in them. There are what we call exact numbers. All right. So for example, if I said how many grams of copper sulfate are in 1 liter of a copper sulfate solution, I mean approximately how many grams are there in exactly 1 liter. So when you see things spelled out, and this is one way you can tell, if it's spelled out 1 liter, that means 1.000 out to infinity liter exactly. All right. So how do I deal with exact numbers? Well, I don't. Okay. I don't count significant figures for exact numbers. Okay. Because there's no error in them. They don't contribute any error to the answer. The only ones that contribute error to the answer are the measured values that actually do have error in them. So I look at those and I don't look at the exact. Now, you know, I still divide by 12 or I still divide by 3, but I don't divide by 3 one significant figure. I just divide by 3. All right. So how do I know if a number is exact? Well, if it's spelled out like this, it's exact. All right. If you see 1 liter and you see in parentheses after that it says exactly, That's a pretty good hint that's an exact number. Right. If it's part of an English to English definition, 1 foot's equal to 12 inches, or, they're 3 feet in 1 yard, or 1 mile is equal to 5,208 feet, those are exact because they're defined that way. If it's part of a metric definition, 1 kilometer is equal to 1,000 miles, those are exact. If it's English to metric or metric to English, with one notable exception, those systems don't line up perfectly, and so therefore it's probably inexact. You're going to count significant figures there. Okay? All right, so watch out for that. Okay, well, I know I can add and subtract, and I know I can multiply and divide, and I know I can apply the rules. The question is, what if I have to add and subtract and multiply and divide? Which rule do I use? Well, you use both of them. You just use it when you need it. All right, so for example, density, of course, is equal to mass over volume. We talked about that. So here's a problem. This is something you would probably do in lab, maybe. Okay. An empty flask weighs 34.256 grams. 15.0 milliliters of carbon tetrachloride is pipetted into the flask. What is the density of the carbon tetrachloride if the total mass is found to be 54.656 grams? Okay, well, let's see here. We know that density is equal to mass over volume. All right, so first thing I got to do is I got to figure out the mass of my carbon tetrachloride. So what's the mass of my carbon tetrachloride? Well, I know the flask weighs 34.256 grams. I know the carbon tetrachloride in the flask weighs 54.656 grams. So all I have to do is subtract off the weight of the empty flask, and that should just tell me how much carbon tetrachloride I've got. So 54.656 minus 34.256. Okay, here I'm subtracting. What's my rule for subtraction? Keep as many places past the decimal point as are in your least precise quantity. So how many places past the decimal am I here? 3. How many am I here? 3. So how many should I report my answer? 3. Okay, so I'm going to write these numbers down, and I'm going to go 3 places past the decimal, so I need to report this as 20.400 grams. Okay, 3 places past the decimal. I know this weighed out to the nearest thousandth of a gram. Volume. Well, that's given to me. That's 15.0 milliliters. Okay, so now I just simply divide. So 20.400 grams divided by 15.0 milliliters. Now I'm dividing. What's my rule for division? Keep as many significant figures. Here's where we use significant figures. So you don't use significant figures when you're adding and subtracting, just when you're multiplying, dividing here, as are in my least precise quantity. So how many do I have here? 5. See, these two count. There's zeros after non-zero digits after the decimal. So 5 here. How many here? Good. 3. So 5 here, 3 here. How many should I report this to? 3. 1.36 grams per milliliter. 3 significant figures. So see, just you don't do the whole calculation, then try to figure out how many significant figures are in your answer. Just every time you add and subtract, apply the rule for addition and subtraction. Every time you multiply and divide, apply the rule for multiplication and division, and when you get done, your answer will magically come out in the proper number of significant figures. That's how you do it. And again, it's a little cumbersome at first, but it's nothing that you can't do. You have the intellectual capability of doing this. Okay, see if you can do this one. What is the volume occupied by 10 grams of carbon tetrachloride? Okay, well, I know that density is equal to mass over volume. So now I know the density of the carbon tetrachloride is 1.36 grams per milliliter. I know the mass is 10, so all I got to do is solve for volume. So to solve for volume, we want to get volume in the numerator here. It's in the denominator. So we're going to, of course, anytime you want to get something the other side, you always do the opposite. So if this is divided by V, I'm going to multiply both sides by V. So I get 1.36 times V is equal to 10. And then I'm going to divide both sides by 1.36. And that gives me the volume. How many significant figures should I have in my answer? 3. Well, why 3? 10 only has 2, right? No. Look at the problem again. How is it written? That 10 grams is spelled out, right? If that 10 grams is spelled out, what does that mean? That means it's an exact number. Remember? How much air is in that 10 grams? Nothing. Exactly 10 grams. The only measured value with error in this problem is this one right here, the 1.36. How many significant figures do I have here? 3. How many should my answer have? 3. 7.35 milliliters. 3 significant figures. So yeah, watch out for that, because on the test, probably not going to have exact with an arrow pointed toward it. Again, how are you going to know if it's exact or measured? I will make it clear, abundantly clear on the test. I'm not gonna throw anything like this at you on the test, where you have to make you have to read my mind. That's kind of hard to do. Okay. All right. Can you do this? Okay. I'll tell you what. We're hitting 30 minutes, so we're gonna quit right here. And then next time we're going to talk about something else. Here comes the math. What if I could show you a way that you could do a problem, and there is no way you could miss it? You just can't miss it. And let's say, because you found a way to miss it, because students are always finding ways to do the impossible. Let's say you missed it. You could check your work. You could find your mistake in 10 seconds. You could fix it. You could walk out of the room knowing that you did everything correct on the test. Wouldn't that be a useful skill? Don't you think we need to talk about that? Well, tune in the next video. Maybe that's what we'll talk about. So, bye for now.